Hello. In this final video for the calculus portion of the course, we're going to look at the original problem that we had on the first day of class about throwing an object and finding the optimal launch angle. So again, if you recall, we're going to assume a flat Earth with a uniform gravitational field and no air resistance. We're going to launch a projectile from ground level with a velocity of v0. We want to determine the optimal launch angle so that the horizontal distance traveled is maximized. Now, some of you argued for 45 degrees, that perfect halfway between vertical and horizontal, and maybe it's true, but how would you know? How could you prove it? We need to have some type of argument here, and calculus will allow us to do that. In particular, notice we want to maximize something. If we can make a function for the horizontal distance, we can use the techniques of calculus to maximize that distance, and then, of course, find ourselves the perfect launch angle. This theta is what we're going to be trying to have our function in terms of. So we have a lot of work to do. Here are some relevant formulas from physics. Vx, which is the amount of velocity in the x direction, is v0 times cos theta, because the x amount will depend on the angle, if you're throwing it all vertical or all horizontal or some way in between. Vy, which is the amount of velocity in the y direction, again, it depends on theta, it's v0 times sine theta. The distance traveled x is vx times t. And the distance traveled in the y direction is vyt plus 1/2 at squared. Here we're going to be assuming that a is going to be 9.8, and in this case it's directed downwards because it is towards the ground, whereas up is going to be positive. Now, if you want, I encourage you to pause this video and give this problem a try on your own. It's quite a fun and interesting problem, so I don't want to take it away from you, but give it a try on your own, and once you're done, go ahead and restart the video and follow along with me. All right, I'm assuming you've given this a try, so let's see what we come up with. Well, we need to determine this. This right here is what we want to maximize. So x equal to vx times t is what we want to maximize. But the problem is that it's in terms of t. And we need to make it in terms of theta, because we're looking at the optimal launch angle. So we need to get rid of that time, and so we need some formula for time. So let's look at this formula here and see if we can figure something out for time. Well, we actually know the time. The time will be done, the object will be done flying over here when y is equal to 0. So let's do 0 is equal to vyt plus 1/2 at squared. We could factor a t, and we'll get vy plus 1/2 at. Well, clearly that means that either t is equal to 0, which is over here at the beginning, so that's not exactly the time we're looking for, or it means vy plus 1/2 at is equal to 0. That, of course, will be the other time. So let's isolate for t. We're going to get 1/2 at is equal to negative vy. So we can multiply by 2. At is equal to negative 2 vy, and t is equal to negative 2 vy over a. Now again, we're going to use a equal to negative 9.8. You could actually do this question without even plugging in for a, but just to give you something to hold on to, we are going to put a equal to 9.8. So we're going to get negative 2 vy over negative 9.8. which is going to work out to the following. T equals vy over 4.9. All right, we found our formula for t, so let's plug that back in, and we'll get the following. X is equal to, well, vx times t, which means x is equal to vx times vy over 4.9. Now, those are not in terms of theta, but we have some formulas for those. We know that vx is equal to v0 cos theta, and vy is equal to v0 sine theta. Now let's get those constants out in front. We don't need those clogging up our formula. So we have v squared over 4.9 times cos theta sine theta. Well, it looks like we now have a formula for x in terms of theta. So we can write this as x of theta equals v naught squared over 4.9 cos theta sine theta. And important to note here, this is a constant. The initial amount that you're launching at, that velocity, is not changing. 4.9 is a constant, and we have cos theta sine theta. So we're good to go with calculus. So let's move it on down and find x prime. Well, the constants will stay out front, except, oh no, cos theta times sine theta, that means we need a product rule. So if you've ever wondered why you need the product rule, well, this question right here requires the product rule. Derivative of cos is going to be minus sine. And then we put the sine theta there. Plus, we'll leave the first function alone, v naught squared over 4.9. And then the derivative of sine theta is cos theta. So we'll factor the v naught squared over 4.9 out of the whole thing, giving us negative sine squared theta plus cos squared theta. Now, eventually, we want this thing to equal 0, and so we should factor this down further, which, if you remember, we have cos squared theta minus sine squared theta. We could do a little difference of squares. So we'll get v naught squared over 4.9 cos theta minus sine theta cos theta plus sine theta. Well, that would mean cos theta equals sine theta, or cos theta equals negative sine theta. Now, where does cos theta equal sine theta? Think on the unit circle. Where are cos and sine equal to the same value? Well, of course, at theta equal to 45 degrees. And where is cos theta equal to negative sine theta? That happens at 135 degrees. All right, well, let's go ahead and draw our Sine diagram. So we're going to get, we have our point at 45 degrees. We know that the minimum launch angle would be 0 degrees, and the maximum launch angle would be 90 degrees. So this point over here for 135, we can cross it out because it's not part of the domain. Now we need to pick a number bigger than 45 but less than 90. So here's our domain. We'll write that down. Our domain is 0 degrees to 90 degrees. And we need to pick one on either side. Now technically this isn't a polynomial, so we can't use our rules of even power, odd power. It's not really clear what power this would be coming from in the cos theta minus sine theta part of the root. So let's just use a test value on either side. So we're going to test here, theta equals to 60, and we'll test over here, theta equals to 30. Well, let's look back at our derivative here. So if we test, let's say, 60, cos of 60 will be 1/2, and sine of 60 will be root 3 over 2. Well, root 3 over 2 is bigger than 1/2, so this is going to give us negative. This is positive, so we're going to get negative for that 60. If we test 30 over here, well, cos of 30 is root 3 over 2, and sine of 30 is 1/2. So in this case, this is positive. This is still positive because we're adding two things. And then the front is positive as well, so this is going to give us positive. Well, let's look at that Sine diagram. It is increasing and then decreasing. So what do we have here at 45? We have a rel max. Of course we do. Increasing and then decreasing. So we can then say that theta equals to 45 degrees is the optimal launch angle. And, well, there you go. We've been able to determine the optimal launch angle as 45. Now, you might argue that this technique is over the top, that everyone knows that 45 degrees is the perfect launch angle. That's so obvious. Since you were a child, you knew to throw something at 45 degrees. And I would argue that yes, if we assume that we are on a flat Earth with a uniform gravitational field with no air resistance, yeah, sure, 45 is the optimal launch angle, but there are many other situations where you might be launching something. Let's say, for example, that there is some air resistance. So you're going to be throwing it into something. Let's say there's a bit of wind. So we could have air resistance. There could actually be air. What if there was wind? What if you were on a cliff? Surely if you're standing on a cliff, you're not going to necessarily want to launch at 45. You might want to give it more horizontal because it's got some distance to fall. What if you had, well, a non-uniform gravitational field? Or what if you were launching an object so hard that it actually was affected by the curvature of the Earth? So what if you had curvature? Because of course, we know the Earth is not flat, and so there are all these other situations to take into account. Air resistance, wind, a cliff, a curve. And what they would do is all of those situations would change these formulas here. So these would all change. For example, if there was wind, then there may be something affecting your Vx. It may be blowing it back, or maybe you're throwing it with the wind and it's being blown forward. If you had some air resistance, there may be some change over to all of these formulas. If you had it dropping off of a cliff, certainly this formula will change because it's going to be going further down before it hits the ground. And the thing is that all of those changes can be handled with the same method here. We would adjust our formulas, do the same work, calculate the derivative, draw a sine diagram, and get our answer. And so all of these situations can now be handled with calculus. I agree with you that 45 degrees, it's a bit overkill to use calculus to come up with that answer. But all of these, which you'll look at in future courses, especially if you go on into engineering, all of these types of situations require calculus. It is not 45 degrees when you have air resistance, when you have wind, when you have a cliff, or when you have a curvature. All of those require very different launch angles, and the only way to determine them, because there's no intuition to use, is to use calculus. Calculus allows us, of course, to confirm our intuition when the answer is 45, but it allows us to go beyond our intuition when the situations become more complex. So I hope you enjoyed this problem, and I hope you enjoyed our calculus course. As always, thanks for watching.